Welcome back, everyone. This is part 2 of how to design a guitar pedal. If you missed the first part, I recommend going back and watching it, but to recap, last time we defined an initial concept for our guitar pedal. We're going to be doing a stereo ping pong delay. We also talked about how we could define the feature set that would really separate our pedal from anything else that's out there. And we also created a block diagram that gave us an idea from a very high level how we want the circuit to function. If you want a refresher on that, please go back and take a look at the last half of the video where we went through not only making the block diagram, but through all of the choices that went into how we got there. Now in this part, we're going to be creating the schematic for our pedal. This is a real-time look at how I create a schematic for a new pedal idea, so it is going to be a little long. But before we get into the actual creation of the schematic, and for those of you who may not have the time to watch through everything right now, let me run down for you the things that we're going to cover. First, we're going to take a look at our block diagram, and we're going to take the functional blocks and we're going to use pre-existing designs. I'm actually going to be using some stuff from my Echo Rec design, which is a 4 delay line pedal, and using some of those blocks in the design to help speed up the process of creating the schematic. If you want to do the same, it's really helpful to go find a pedal that is similar to what it is you're trying to create. For example, with a PT2399, you might go look at something like the Deep Blue Delay from Mad Professor. That's a really good one. And if you want to find those schematics, if what you're building is based off of a commercial design, I really love the websites pedalpcb.com, Aeon Effects, and PCB Guitar Mania, because they take commercial pedals, they reverse engineer them, they sell the PCBs for them, but in their build documentation, they include all of the schematics for them. Also, it would be helpful in our case of using a PT2399 to go and read up on the ElectroSmash PT2399 circuit analysis page. That will help give us an understanding of why the bits and pieces are where they are and what they do. In particular, you'll hear me talk a lot about a multi-feedback filter topology. And so if you go and just look at how that snippet of the circuit works, it could be really helpful. One thing you'll notice throughout the creation of this schematic is that I make a couple of changes from our block diagram, just because we are now starting to think about the specific implementation of the effect. We're starting to put actual components and values in. And so as I was going through and looking at it, there were a couple of things that I decided to change here and there. For the most part, it's going to stay very true to our block diagram, but there are a couple of small changes there. I have done my best to break down the schematic creation by functional blocks so that it's really easy to follow and really easy to relate what I'm doing in the schematic creation back to what we had done in our block diagram. And in the end, I think you'll see that they really do tie together quite well. So for our schematic today, I'm going to be using Eagle. There are lots of great circuit design packages, including KiCad, pads, dip trace, easy EDA. There's probably a lot more that I'm not aware of. But I use Eagle just because it's what I first learned, and a friend who helped me learn was a regular Eagle user, so it was just really easy. For what I do, the free license is fine. I prefer 2-layer boards because they're really cheap to have made. And the 4x4 inch maximum board size is usually plenty for most guitar effects. It won't work for something like really gigantic, but if I need something that's a really big circuit, usually I'll do 2 stacked boards anyway, just so that I don't have a huge enclosure. So here I have my blank schematic page. In the free version of Eagle, you only get 1 page, but it can be more or less infinitely big by using the zoom in and out and panning controls. And I like to lay out my circuits kind of like the block diagram. I go input on the left, output on the right. Um, and so I am going to start off by putting in a bunch of just really common components. And these components are going to be solder pads, some of the main chips that I'm going to put in, stuff like that. So first I'll go grab some solder pads. I like to do the 1mm solder pads, the 1mm hole. And I'm going to have my input there. I'll do power and some pads down here. I'm really just throwing things in really haphazardly right now just to kind of get them there. So there we've got some solder pads. Okay, so next I'm going to go ahead and drop in some ground symbols. I use the A ground from SparkFun just because it'll automatically tie these to ground when we go to design a PCB. And then I know that I'm going to need some op amps. I'm going to go ahead and use a TL074. Oh, that's because, there we go. And I'm going to try and do everything through hole for this. We'll see if we can get it all to fit through hole in a 125B enclosure. So I need an op amp for my input buffer. I need an op amp for the output summing amplifier on the left and on the right. And then we're going to just put our fourth op amp there. Now, if you're using Eagle, one thing that I highly recommend is to go get the Mad Bean libraries, because there are all kinds of great libraries that he has for things that are very common for pedal use. So, for example, I think he's got a PT2399. He does. So there's our PT2399. Oh, I have not selected the right footprint. There we go. It comes out really big so that you can have lots of space for putting all of your components in the schematic. And let's see, then I'm going to go ahead and just drop in a couple resistors and capacitors just to get us started. I'm going to be using our capacitors that are, let's see, this is a new installation, so I'm having to figure out where to put some of these things. We want the 50, let's see, is this going to be right? Nope. We want the 50 thou spacing on them. That looks right. Yep, that'll be it. And so I'm just going to put a couple of those guys here. I'm going to grab some of the, let's see. Which ones are these? That's our normal 1/4 watt. And so I'll just drop a couple of guys in here. And then we're going to start moving things around a little bit. So I'm going to zoom out so I can space some things out so that we have room for everything. Go like that. Like this. Let's see. We'll also move our input up a little bit. these guys up. Okay, so now what we're going to do is we're going to start taking advantage of some previously existing building blocks. I could go into some of the previous designs that I've done and pull from there. Another thing that I'll do is if I'm working on something that is at least somewhat related to a commercial pedal, I'll see if I can find the schematic online. Places like Pedal PCB and PCB Guitar Mania and Aeon Effects. Those are really great places to go find high quality schematics of commercial pedals because they've opened them up, they've reversed engineered them, and now they provide PCBs for them. But in my case, I'm actually going to go and just kind of use one of the input buffers that I use on one of my own projects. I'm going to just pull this guy up into here real quick. So this is for the Echo Rec, which was one of my first big projects. And this is what my input buffer looks like. It's a simple inverting gain stage. It has a pull down resistor that is going to drain off this input capacitor when we don't have any signal going to it. And then the ratio of these two resistors is going to set the gain in this system. This right now has a gain of just under 2. And then this capacitor right here is going to help stabilize the high frequency performance and is going to allow us to get a little bit of high frequencies back so that we, maintain good stability and everything. So move that back out of the way. We're going to take one of our resistors here. And this guy's going to be our pull down resistor. This will be our input capacitor. Let's see, pull that down. I also need to give him a little more space so we can bring in this resistor. And then we're going to copy this resistor so that we have a resistor in our feedback loop. Whoops. Yeah, actually that'll work. Just copy over this capacitor. And now I'm going to, actually I'm gonna make this so that this guy lines up here. I get a little crazy sometimes about making sure that things are really nice and clean and organized in my schematics. I find it helps me just make sure that I don't mess things up as bad. Oops. We're going to go there. I'm actually going to zoom in here a little bit, make my life a little bit easier. Let's see, let's go ahead and get rid of that funky line. And we'll go like this. This is in our feedback loop. And so we'll do that. We're going to just pull a net out here. I'm going to give it a name. This is going to be Vref. That's going to be our reference voltage. That's how we're going to bias our op amp input there so that we have plus minus voltage swings available to us. I'm going to take our ground symbol here. We're going to move him right up there. I'm also going to, on this op amp, I'm going to show my power pins. That guy goes to ground. This guy's going to come up here. And there we go. Now I'm going to name him. This is plus 9 volts. That's my supply for my op amps. And so now we've got our input buffer all complete. We have the architecture all complete here. So that stage is done. Next, we're going to move into our delay stage. The reason I do this is I like to keep the part numbers so that they get bigger and bigger as you go across. And so I don't want to have like R4 be all the way over at my output buffer necessarily. Again, that's just kind of a personal preference thing. You are welcome to set it up however works for you. I'm going to give ourselves just a little more space to work with here. All right. Now you'll notice that the pins along this side of this particular package don't correspond to the physical pins. We have pin 1, 2, 6, 7, 8, 3, and 4. That's done just because it's convenient for these ground pins here. So what I'm going to do is I'm going to come and grab myself another ground symbol. Just put him here. Tie our grounds in. For our PT2399, we're going to, I'm just going to have essentially a bank of capacitors here. So there's that capacitor. I need an electrolytic capacitor. Oh, let's see, and I want one that is going to be, this is going to be a 47 microfarad capacitor to stabilize the analog reference voltage. So I'm going to pick a 6mm diameter electrolytic because we can easily get a 6mm 47 microfarad. And then we're going to take another couple of these film or ceramic capacitors, whatever we want them to be. I'm actually going to go like this. And I'm actually going to make it so that they all line up nicely. Get all our caps in a row. Because all of these caps are going to end up being grounded on one side. We will go like this and like this. And we've got one cap that's going to go here for our demodulator, one here for our modulator. That barely fits. This cap is our power decoupling cap. This is going to be placed locally to the chip so that it can help smooth out any issues with our supply, our 5-volt supply. There's that. And now we've got all this open room for our time control here. We're going to put in a resistor here. This resistor is going to make it so that there is a minimum amount of resistance on our time control pin, because with a PT2399, if you don't have a minimum amount of resistance, the chip can actually lock up and it's not going to work well for you. And now we need a time control, but because this is our first delay stage, we're actually going to be doing this as a dual gang pot, like we had in our block diagram. So I'm going to go to the Mad Bean potentiometers, 16mm. Oh, nope, dual gang. And 16mm dual gang. This will actually pop up what looks like two separate potentiometers, but they're actually connected to each other. So there's that guy. You see it says pot 1A, and this one will be pot 1B. And let's see, we'll actually wire this guy up. So this potentiometer is going to be wired up as a variable resistor, which means that this lug is going to actually be connected. The wiper lug is going to be connected to one of our two outer lugs. And because we want this to be a higher resistance, as lug 2 turns all the way clockwise, that means that what we want is we want lug 2 to be connected to lug 1 because, oh, nope, let's see. Because we want to have the resistance get larger as we turn clockwise, that means we want the resistance between 2 and 1 to get larger as we go clockwise. And all the way clockwise, 2 is connected to 3. So we're going to come around and do this. Just like that. Beautiful. Okay. So that is it for this side of the chip. Now we move on to the other side of the chip, where we have 2 op amps here that are set up for filtering of our modulator and demodulator. Our actual delay output is going to come off of pin 12. We're going to use the this op amp on pins 15 and 16 as our input filtering, and we're going to use this op amp for filtering our output. Okay, but we don't need to reinvent the wheel. In fact, we can actually come and take a lot of what is from a pretty common delay stage. So I'm actually going to bring this up here real quick. This is one of the delay stages from the Echo Rec. We have a capacitor that we come through, and then this arrangement of going through a resistor with a cap to ground, and then through these other 2 resistors into the in and out of an op amp is what's called a multi-feedback filter topology. To learn more about this, I would highly recommend that you go to the Electro Smash PT2399 analysis page. This is really great. This talks all about how the PT2399 actually works. And he comes and describes a little bit about the multi-feedback configuration. If we come down here to the right section about the input. So there's the input stage. And so we've got a low-pass multi-feedback filter. Okay? But the wonderful thing about this is that there are online calculators for this. Here he's got a link where you can actually see this is the topology for a multi-feedback low pass, and then you can put your values in here to figure out what your cutoff frequencies are going to be. For most PT2399 delays, the input is set up with a multi-feedback, and it's really common to have them set up something roughly like this, but I'm not worried about values right now. Right now, I'm more worried about getting the architecture all put together. So I'll pull that guy off, and we are going to get ourselves some components here. So what we're going to do is we're going to put our capacitor there. We're going to go ahead and take our resistor here. So this might look a little weird at first, but we're going to take this guy. In fact, we're going to take him way out over here. So this is going to be our signal from the buffer. This is our first cap of the multi-feedback. This cap down here needs to go to ground. So I'll go ahead and just copy my ground symbol to make it a little more compact here. Oops, I put that in the wrong place. Look at me go. This guy actually needs to come off there because that's how we work. Okay. But now we also have a resistor that comes into pin 16 and into pin 15 because those are the ins and outs of our op amp. Connect these guys to their appropriate inputs. This will come over here. We'll go like that. And next up, we need a capacitor between these two pins because what this is going to do is set some more filtering for us. So we're going to go like that. Beautiful. We're also going to take a capacitor and put it across here and one across this pair of pins. This is necessary because this is setting filter cutoff frequencies for the modulator and demodulator in the digital to analog conversion and the analog to digital conversion. And so the value of these caps will help reduce any high frequency noise that might get that might otherwise get into our signal. There we go. And now, because pin 12 is our output, we're actually going to set up another multi-feedback filter on these pins. So we need to take our signal that's going to be our input to the op amp, which is going to go through a resistor here. It's going to go cap to ground. It's going to go through a resistor to the input and through a resistor to the output. Whoops. Didn't quite connect there. There we go. Oops. There we go. And we need our capacitor here to go to ground. And we also need a capacitor between these two pins. For the sake of our filtering. And now what we're going to do is our output now comes off of pin 14 because this is the output of our multi-feedback filter arrangement. So first, we're going to give this guy a little RC filter. Okay, just really basic. This is how a lot of the commercial pedals that say analog delay or that say analog voiced delay, this is how they voice it for analog, is they're actually going and they're rolling off some of the high end from the repeats. Okay. This guy being an RC filter is just going to come down here like that. Beautiful. And then we're going to put in a DC blocking capacitor before we send our signal anywhere else so that any DC that might be riding on our output of this op amp gets filtered out so that we only have the AC portion of the signal. And obviously we are going to need to move this guy. But now we have a complete first delay stage. Okay? We'll need to come in here, we'll need to put in some values in a little bit, but for right now, we just want to get the architecture all put together. Now, because we're doing this in series, we're doing series delay lines, we're actually going to take the output of C15 here, and it's going to become an input over to here. But we are still going to be doing a multi-feedback filter arrangement. We may actually end up tweaking the values either of this RC filter that's R11 and C14, or we may tweak the values of the multi-feedback filter so that we make sure that we don't have too much high frequency roll off, right? Because if we low pass filter here and then we low pass filter on the input, we might be introducing too much high frequency roll off so that we end up getting a really weird kind of reduction in high frequencies going from left to right. And if we keep that up, we'll continue to get that degradation as it goes back and forth. And a ping pong delay is meant to be very kind of crisp. So the actual values, we'll play with those once we get on the breadboard. But for now, we're just going to go ahead and put in the structure here. Now this C7 was our DC blocking capacitor out of this buffer before going into the multi-feedback. So C7 and C15 are performing the same role. So I don't need another capacitor right here in front of R12. In fact, first, let's figure out how much space we need on this left-hand side of this guy. So let's get some capacitors in here. We need one there. We need one there. We need one over here. We need another electrolytic over here. You can see that I'm leaving some space. Oops, I don't want to copy that guy. I'm leaving some space so that I can have clean labels going on, because I really don't want my labels to get all kinds of messy. Now, this guy might interfere with my output there, so I'm going to shift everything a little over here. That's still probably plenty of space, which means I might be able to shift this guy a little bit like that. Let's see what we get. That looks like it ought to work great. So we'll just connect these guys up to ground. Okay. Let's see. I'm actually going to move this guy over a little bit, because I just remembered we, on this second delay stage, are going to need to put in basically two different time potentiometers, because we need to be able to take this guy or his own independent controls. So let's grab a 16 millimeter bottom mount potentiometer. We'll put him there. And what I'm going to do is I'm actually going to put in a DP/DT toggle switch for my mode switch, because I know I'm going to want this mounted on the top of my enclosure. So we'll go to switches, DP/DT. I'm going to go with lugs because those are the ones I usually use. No other reason than that. Okay. And then what this means is that our pin 6 can be connected either to his own independent potentiometer or to the second half of our dual gang potentiometer for time 1. These guys are going to get wired up exactly the same, just as a variable resistor. Now, before I get too far, I'm actually going to save this, because I haven't saved this schematic yet, and it would be a shame to lose it. I am going to actually create a new folder here. I'm just going to call this ping pong for now until I get a name for it. And this will be ping pong _th for through hole. There we go. So now that's saved, I can continue working and not worry too much about possibly losing all of that work. Working at my real job, I learned the importance of saving and backing up in a very painful manner when several weeks worth of work got lost because my hard drive decided, my spinner hard drive decided that it was going to catastrophically self-destruct and I couldn't get any data off of it. It made me very sad. Okay, so now that we know what our spacing looks like on that half of the chip, we're going to come back to our multi-feedback arrangement. We need resistors on both of those. We're going to need a cap there. We're going to need a cap here. 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 Let's see, I'm actually going to give myself just a little more space. Just so that my label doesn't interfere there. Beautiful. I'm also going to need another ground symbol. Start connecting all of my various things together. When you're making your connections, it's important to make sure that you're actually making the connections. So like in Eagle, you've got these little dots that show that, yes, those traces actually do interconnect. I've run into issues where I thought things were connected, but they weren't. All right. So now we need to create our multi-feedback arrangement off the output of this op amp. So we're going to go like that. We're going to need a resistor there and a resistor there. We're going to need a capacitor to ground. And then let's connect this up so that we've got our multi-feedback filter all squared away. Oh, see, that guy didn't connect. Get rid of that. And let's make sure we actually get it to connect this time. There we are, that's all connected. We need a ground, and our output multi-feedback is complete. Let's go ahead and hook up our output of stage 1 and input of stage 2. And now we are going to take our output of stage 2. We're going to give this guy just a little RC filter again. We're not going to worry about values at this point. Oops. There we go. This goes to ground. Fantastic. So now we have an output coming off of here. And we need to start looking at how we're going to be doing the mix stage. Okay, how we're going to be doing our mix controls. So what I don't show over here is that there's actually going to be a mix control for this output, right? Because this is our first delay output. Because this is stage 1, I'm going to want another dual gang potentiometer. The first part is going to come here. I'm going to go like that. I'll drop the other one over here. I'm actually going to mirror this so that we have our signal coming in on 3, coming out on 2. This is going to run all the way over to meet up with our left output buffer. And then, oops, there we go. We're going to have ground connecting lug 1 of this pot. Okay. Actually, just for the sake of good design, we're going to, and maybe possibly overkill, we're going to make sure that we have a DC blocking cap here, just to make really super sure that nothing's going to come in on here and mess us up. Okay. All right. So now that we've got that mix control going on, let's see. Let's move over. Oh, there's my mouse. Let's move over to here. We need to make ourselves a little more space. Okay. All right. So I'm going to put him here. We're going to now get his independent mix control, which is going to go right here. I'm going to move these guys down a little bit. Because I need the second half of my DP-DT switch. Where did I put it? Let's see, where is it? There's the second half of him. Go something like that. We need our DC blocking capacitor. We're going to bring this guy over here. And let's see, so I have 1 being the independent control and 3 being the dual gang. So in order to not cross the streams, if you will, I'm just going to swap these guys around. So 3 is going to come to the dual gang, and 1 is going to come to the independent control. Okay. And then I'm going to connect these guys both to ground. I'm going to give them their own little ground symbol over here, because we still have to put in the feedback pot, and I don't want to be running, I don't want to be crossing my nets on my schematic any more than I have to, just to try and keep it clean. There we go. We're going to save real quick. Now we need our feedback control. Now, here's where we start trying to make our best guess as to what we want our feedback control to really do. Do we want this to control the level between delay stage 1 and 2, like we talked about in our block diagram, or do we just want to have the same amplitude repeat on left and right and then reduce? I think I want it to reduce in amplitude every time it repeats, whether it be on left or right, just because what that's going to do is make it sound like it's actually bouncing from side to side and you get a little bit of that level loss. So there's that, and we're going to need to put this guy over here. Okay, so let's go ahead and break up that net real quick. Let's actually rotate this guy like that. There's our input. this guy is going to come over and be the output of this pot. And then we need ground. We're going to connect him up. Now, the chances of us needing the same value pot here and here to make things sound right is kind of low. So just to kind of hedge my bets, I'm going to put in a resistor here that is going to go on either side of the lugs, and what that'll do is that'll give me the opportunity of changing exactly what this pot value ends up looking like. Let's get rid of this guy here. We may not actually need this, but I'm just going to put it there for the time being just to be safe. We are going to go ahead and take our feedback here. Now coming out of the feedback, we could do some filtering if we wanted to. It's not uncommon to filter the feedback, particularly with something that's going to be analog voiced, because you want each subsequent repeat to lose more and more high frequency. But I think we've got enough filtering here and on the output of the first stage and between the first and second stage. So what I'm going to do is I'm just going to put that to ground. I'm actually just going to name this. This is going to be FB for feedback. We're just going to put them right here. Now our feedback is actually going to come in. It needs to come in over here, right? So if we were to look at, say, a traditional PT2399 delay, like the deep blue delay from Mad Professor is really common. Here's my Google search for deep blue delay schematic. I'm just going to find one that I can look at really easily here. So if we look at this guy, we'll just take a quick look at, here's our output, here's the feedback. They voice the feedback a little bit through here, but then it goes into pin 15 and 16 right here after the first resistor of our multi-feedback. So let's go ahead and do a similar setup here. We're just going to go ahead and take our capacitor and a resistor. Ooh, those guys are getting a little tight. Let's go ahead and give them some space. We'll go ahead and go like this, and then I can put him like that, and put this guy like that, and we're going to and then when we name this feedback, or FB, it's going to say connect them, yep, and now this spot and this spot are connected. We're going to save there. Good. So now that we have our feedback all wired up, all that we really have to do to finish off our audio path is to wire up our, or to create our output summing amplifiers for both the left and the right. So we will, let's go ahead and do something like this. And we're going to go there. So what we need to do in order for this to be a summing amplifier is we need to have both of our inputs that are going to come in have a resistor. That this resistor value will work in conjunction with the feedback resistor to set the relative gains for each of the signals in our output buffer. I'll explain that here in just a second once I get the structure set up a little bit so you can see what I'm doing. So with one resistor, we're going to have this be our dry input, and then R22 is going to give us our delay signal input. And then R23 is going to be in our feedback path. We're going to have another small value capacitor right here. I'm actually going to bring him down just a little bit so that it's not interfering there. So the value of this resistor and the values of these resistors will set the gain for each signal. This is using something that's called virtual earth summing. It has to do with the way that an op-amp works, where it tries to keep the voltage at each of the input terminals and the output terminal the same. So because we're using the negative input, we need to provide a reference voltage onto our first terminal there. When we get to adding values for everything, R21 and R22 are actually going to be the same value, because what that means is that with a maximum mix signal coming out of the delay stage, it will be the same amplitude as the dry signal. So maximum mix will be dry and wet in equal measure. And then so we're going to add ourselves a DC blocking capacitor here. Make just a little more space. And then we're going to put in a very small voltage divider here. This isn't going to do very much to the actual signal level. It is more just here to provide a controlled path for this DC blocking capacitor to discharge when when we don't have anything coming through the audio path. This will help with reducing the occurrence of pops when we switch the effect on and off, and then this guy goes to ground. And now we're going to do exactly the same thing for the right side here. We're just gonna have to, let's see. Oops. We'll put him there for now. Let's see. So, okay. So what we're going to do is this will be very, very similar to what we did above, except that because we have oh, those mix pots are wired up incorrectly. Because we have two different mix pots, they need to each have their own summing resistor. I did that totally wrong. Okay. So we've got our two different mixing resistors there. I'm going to kind of rearrange how this was done just so that just to make it look a little cleaner. So let's see, how do I want to do that? We're going to go ahead and we'll put that there, there, and there. When you're doing a summing amplifier on an op amp, it can be really handy to put all of the mixing resistors in an arrangement like this, because then you can just look really easily, really quickly at what the values are to get an idea of what the relative signal level is going to be for them. And we need our little capacitor here. When we get to actually setting values, we're going to want these buffers configured identically left and right, because we don't want them to be changing either the level or the filtering between left and right, because that can mess things up. Let's go ahead and finish getting our components in here. And we need this DC blocking capacitor in there. We're going to go ahead and get these guys connected like this. And let's grab a ground signal, or a ground symbol rather, and hook him up. Okay. Whoops. So now once we get our mix output set up, we will be ready. Well, we need our dry signal too. We will have our audio path, our signal path, completely done. Let's go ahead and move this guy a little bit. And he's going to go there. Let's move him just a little bit like that. And I'm actually going to move these resistors just a little closer to make my life a little easier. Having a nice clean schematic is really great for when you come back and you're needing to troubleshoot or you're needing to reference something. So trying to make it as tidy as possible is always a good idea. Also, if you ever share the schematic with anyone, they will thank you for not making a horrible, unreadable mess. If you go look at some of my projects, you'll see that my my schematic style has evolved somewhat over the course of doing my projects. There we go. So now, if we zoom out a little bit, you can see that we can break this down to look a lot like our block diagram. This is our input buffer that we had talked about in our block diagram. Here's our output summing amplifier for the left side, output summing amplifier for the right side. We have our first delay stage that has his time control right here and his mix control right here. This is our second delay stage. It has two different time controls that are governed by a switch, and two different mix controls governed by a switch. We have our feedback coming off of our second delay stage and being fed back into the first delay stage, so that we get the left, right, left, right, left, right decay. And then we also put this this level control between the two stages. All right, so with that, we can now turn towards our power section. This will be pretty quick and easy because a power section for a circuit like this is going to need 9 volts in. It's going to need a 4.5 volt reference for our op-amp stages. It's going to need a 5 volt regulated supply for the PT2399s, and it's just going to need some really basic some filtering and reverse polarity protection and stuff like that. So we are going to need a couple of resistors for our reference voltage. Let's zoom in a little here. Move some things around a little more. Now you see all of these different solder pads here. These are going to be, most of these are going to be for the various ground connections that'll be on the board. Let's go ahead and move this guy. Copy. We'll go like that. We also need some electrolytic capacitors here. We're going to have one for helping regulate the 9 volt, one for regulating the 4.5 volts, and one for regulating the 5 volts. We're going to go ahead and move our ground symbol down. Let's go ahead and connect up our grounds. Whoops. Because all of these guys here are all going to be grounds. This will go to ground. This will go to ground. This will go to ground. We'll come and bring the 9 volts in here like this. And now we need to add a voltage regulator. So I like, for this case, we'll just use a 78L05 regulator because it comes in the TO92 package. It takes up very little space compared to the bigger TO220s. We'll just put them right there. We're going to give him, oops, let's move him down so that everything looks nice and pretty. There we go. And then we'll do that. Bring his filtering capacitor over here like this. And then connect that to ground. And now what we're going to do is we're going to label these different nets so that they tie in to the voltage rails that we have specified before. So now we know that this 9 volt in needs to go to our op amps. This 4.5 volt reference voltage needs to go to all of our buffers. And this is going to be plus 5 volts, which we need to also connect to pin 1 of each of these PT2399s. Okay. Now the last thing I'm going to do here is I'm going to get a couple of different diodes. First I'm going to grab an indicator LED just for the sake of, oh, here we go. Just for the sake of having it in the schematic. We're going to, I'm going to find the right footprint that I like. I like that one. That one's pretty good. Okay. And we'll go like this. And because certain people like different colors of diode, of LEDs, I'm rather partial myself to blue ones because I'm colorblind, and blue is one of the few colors I can see. Let's see, I need a, if we go into potentiometer, I should be able to find the right trimmer. I don't like that symbol, I'll use that symbol. That's the one I like. And we'll just put him right here. we're going to wire it up as a variable resistor. That way this current limiting resistor can be dialed in for whatever the color of the diode is that we want. For example, blue ones, I usually use 22K. For red, I'll use something more like 4.7K. So it really kind of depends. The water clear ones, I'll use really big resistors because those things are super, super bright. And now we need some reverse polarity protection. So I'm actually going to break up this right here. And I am going to look for a 1N5817 Schottky barrier diode, because it has a very low forward voltage drop, about 1/4 volt, and if reverse polarity stuff gets connected up, this guy will blow and it won't affect anything downstream. So there we have that. We're going to save it real quick. And now we have something that meets everything that's in our block diagram. We do still have this extra op amp right here. And I'm actually thinking that what I might want to do is I might want to have an LFO in here that I can switch in and out of, connecting to the pin 6s on my chips to add a little bit of modulation to the delays. And I just noticed something that I'm going to change here real quick. So we have this resistor that sets our minimum resistance on pin 6. I forgot it over here, but I'm actually going to change where this is, because if I want to use an LFO, the LFO is going to be best positioned between the time control pot and this resistor. So, and the reason for that is because you don't want your LFO connected directly to the pin 6, because that can do weird things. I've had cases where it's really messed with the behavior of the circuit, but you also don't want to put it where it's connected to ground on the other side of the pot, because then you're just grounding out your LFO and you get no effect from it. So we're going to change our arrangement to look like this, which means that over here we're going to get rid of these guys. Because they're both doing the same job, what we can do is actually just have them use a shared resistor going to ground, because when one of them is in use, the other one is completely disconnected, and we don't have to worry about any kind of weird interactions between them, and it saves us one resistor so that they're not both having, you know, an independent resistor, because this is just setting a minimum amount of delay time so that the chip doesn't lock up. And presumably it would be the same for both of our potentiometers. Okay, so let's go ahead and save that. For the time being, I'm not going to put in anything for the LFO here, because I want to play with some things on the breadboard first. And after we play with things on the breadboard and figure out what we think things might want to be, then we're going to go ahead and, you know, change the schematic. We'll, you know, put stuff in here. Now I'm going to really quickly come in and I'm going to just put some values in. And these are all just kind of, they're either best guess values or they're values that I've used before that I know will work. and now we're going to start putting in names and changing the labels just to clean things up some, because right now things are a little messy. So we're going to name this as in. This will be plus 9 volts. This guy is actually going to be, this is going to be LED, because that's going to get connected to our foot switch lug. We have ground. We have ground for the input. We have ground for the output. We have, I'm going to call this switch because this is the switch ground for our foot switch. So this guy will get connected to this guy on our switch, causing our LED to light up. Okay, and let's name our output lugs real quick. This is going to be out right. This will be out left. We're going to name our controls. This will be mix 2. This will be mix 1. This will be FB. This will be time 2, and this will be time 1. With the way that this dual gang potentiometer is set up, if you name one half, the other half is going to get the same name, just with an underscore and which side it's on. So now if we pull out, is there anything left unnamed? Looks like all of our controls are named. Okay, so now let's just really quickly go in here and organize our labels so that the schematic is easy to read, which will make our life much easier when we get to the breadboard stage. We take one last look to make sure that everything looks nice and neat and tidy, that we're not cutting anything off, and everything looks good. So with that, we have ourselves a finished schematic. Make sure you save it, and now we are ready to move on to the next stage, which is prototyping on the breadboard. So there we have it. We've now got our full schematic, and we have also identified some things that we want to play with on the breadboard. For example, we want to play with that signal attenuation level between delay stages 1 and 2. We want to look into some of the specific component values. We want to also look into adding an LFO or some other kind of modulation onto our delay time to see what it is that we really want our pedal to end up being. A ping pong delay doesn't usually have modulation on the repeats, but maybe we want to have that as a switchable option. We'll also look at tuning specific values for things like filter cutoff frequencies to make sure that we keep kind of that nice clean delay effect that ping pong delays are known for. I hope you enjoyed this video. If you did and you haven't subscribed already, please do. You'll be notified when the next part comes out, which is where we're actually going to look at the circuit on the breadboard, and I'll walk you through some of my steps and my process for dialing in the values and experimenting with new features on the road to creating a new effect. Thanks for watching. We'll see you next time.